Hello ladies and gentlemen, welcome to my lecture series Modern Gauge Theory. Now this lecture 3 we will talk about the gauge theory of the electromagnetic interaction. Quantum electrodynamics is one of the best theories we have in physics. Here theory and experiment coincide completely. In the gauge theory of the electromagnetic interaction we talk about a U1 gauge group. U means unitary operator and 1 means the operator depends on one parameter. And these unitary operators, as the transformation operators, they form mathematically a group. And so we talk about a U1 gauge group. First, we consider a global gauge transformation. Okay, in quantum field theory, we describe particles by wave functions, psi. And psi is in general a complex function and it consists of several components. K, perhaps. Yeah, X is a 4-vector in the Minkowski space. In the flat Minkowski space, we do not consider curved spaces now at the moment. Then we know energy, momentum and other quantities can be measured of the particles. But the phase of a wave function cannot be observed. And so that is a fundamental principle here now. Physical laws must stay unchanged under a phase transformation, because phase transformation changes the phase, but the phase is not measurable. So, under a gauge transformation by a unitary operator here, the Lagrange density function must stay unchanged. And so, we have now here for the lambda is a real number, and it is represented by a complex E function. The absolute value of such an E function is 1, so that is why it is called a unitary operator. It must be unitary, because else we would get problems with the conservation laws. Now, lambda here is constant. That means we have the same value lambda at every point in space. And then we can write for the transformation here. The old wave function goes over to the new psi prime. And so we apply the unitary operator here, E exponent I lambda, to the wave function psi. Okay, here we have the adjoint version. It is always possible to write down the adjoint equation. If we have scalar functions, then the adjoint version would be reduced to the complex conjugated version. And though, because of the same value of lambda at each point in space, we call it a global gauge transformation. Then the Lagrange function L, or here we have a Lagrange density function, depends on the fields, and the derivatives of the fields, because here we have as the generalized coordinates the wave functions and the first derivatives. So we can write for the Lagrange density, now we have the easiest version here, we write down the wave function, the adjungated wave function and the derivatives. This function must be equal to the transformed function, to the transformed Lagrange density function. Here the things are written by a prime. We consider the first derivative under a global gauge transformation. That means, the transformed wave function or derivative of the wave function is the old derivative and the unitary operator applied to that, or here the adjungated one. And here, this transformation does not cause any problems, because if we write the derivation applied to the transformed psi function, that would be the same as when we apply the unitary operator to the derivative of the wave function. Here the operator and the differentiation, they are interchangeable because u does not depend on the space-time coordinates. But now we consider a local gauge transformation. The parameter lambda in the unitary operator here can have other values from different points in the space-time continuum. That makes no difference of that what we measure, what we observe. And so it must be possible to work with parameter that is dependent on the space-time coordinates. So the Lagrange density function must be transformation invariant again. So we consider the local gauge transformation. That means now the same like before, but now as the unitary operator or the parameter lambda depends on x, the space-time coordinates. Then we use here E, the electric charge, as a proportional factor. So we write instead of lambda here, we write a capital lambda with the factor E. E has usually the elementary charge, because if we consider normal particles, electron, proton, and so on, they have a positive or negative electrical charge. And now we have for the derivatives of the wave functions the following. This is the transformed one, and we get it by apply the unitary operator to the original function. So, and if we write this in this way here, so we must apply the product rule of differentiation, because u now is dependent on x. So we have here two addends. Here in the first addend, psi is differentiated, and here in the second term, u, the unitary operator, is differentiated. So, or the adjungated version here. Now we have the problem that this is not transformation invariant because of the additional term here, which is caused by the space dependence on the parameter lambda. We usually work here with infinitesimal transformations. So we consider now the infinitesimal change of wave function psi. We can write then for the variation delta psi this. This results from a Taylor expansion. If we write here for the unitary operator, here E exponent, i.e. lambda, we have then these idents here, the first ident of the series, and we only take the first two terms and we neglect all the others. So we have here the structure, origin function plus the change. So these are the first two idents applied to psi. That means we have psi plus the change of psi here. 312 here. Okay. If we look at the change of the derivative of psi, then we have this. For the general transformation variation of the Lagrange function, we can write this. This is the same only for the Hermitian conjugated terms. And if we write down that, now we must write down the missing terms here. We write for delta L, that is now the change of this part. This is a variation according to the generalized coordinates, the wave functions and the derivatives of the wave functions. And we get now here an additional term which resulted by the space dependence of lambda, and so we have this additional term. We know that this term here would vanish. That is the expression for the global gauge transformation, but here we have now a local one, and so the second part does not vanish, and that means we have a problem. Delta L must vanish because we must have a transformation invariance. So here first we can say this term here stays, and we know that from basic quantum mechanics here. This is the structure of a current. So we can write now E stays as a factor, and the derivative of lambda stays here, and then this is J or minus J, a current. And now the question is, how can the problem be solved? We have here a current that is a hint that we have perhaps other fields which are necessary here. So we introduce now the so-called covariant derivative. The usual partial derivative is written by this d, and now we want to write the covariant derivative by a capital D. And the covariant derivative is defined now here in 318. That is the usual partial derivative plus an additional term with a new field a mu, or the adjuncted term. Now, if we consider first the commutator perhaps between two covariant derivatives, then we will see, oh no, they do not commute, because the result is not 0 here in the commutator. Now we consider the transformation again of the derivative of the wave function psi. So we again write this, but now we have exchanged the normal partial derivative by the covariant derivative, or here in the adjuncted term. Then we first could look at the transformation law of the gauge field A. We substitute the covariant derivative now in this expression here. That means we have, here this is a transformed version, so this is the transformed covariant derivative, here A prime. And this is a transformed psi function. Then that must be equal to this. This is the original wave function with the untransformed covariant derivative, and this derivative is transformed by applying the unitary operator here. Okay. Now we consider the second and third term here in 321. Here we solve the parenthesis, so that means we have the partial derivative applied to u and psi. Both are dependent on x. That means we get two addends. Here in the first, u is here together with the derivative, and here we differentiate psi. And then we have a third term. That means only the product of IEA and u psi here. Then on the right hand side of the equation, we have the unitary operator who is applied to the differential and psi, that's the first part, or the other addend here is with IEA, that is this one. Okay. Then here we can cancel out a term because it's the same term on both sides of the equation. Here this second addend here and here the first addend on the right side are identical. We cancel them out. And then we also cancel psi and make out of the equation a pure operator equation. And then we multiply by the inverse operator u exponent -1 from the right side. So that means we have here d mu operator and inverse operator. Then this is cancelled. Here we have IE A prime, and we have operator and inverse operator. That makes 1, so here is no operator. And then here this is cancelled, and here we have psi is cancelled out, and so we have a inverse operator here at the right. We want to know A prime, the transformed A. And so we solve the equation for A. That means we have this term now here at the other side, and we have divided by the imaginary unit I. So then we have 324 here. And then we use the following identity. This is the same like this. That is very easy to show that this is true. You have to substitute u, or the inverse of u, and then an easy calculation shows that is right. Exercise for the students here. And so we have, instead of this last term here, instead of this, we have this. And that means we have on the left the unitary operator and at the right the inverse operator and something in between. And though we can factor out the two unitary operators, on the left side we can factor out u, and on the right side the inverse operator, and we have divided by e, and so we get this 325. And now this is now the transformation law for A, the gauge field. Yeah, we now can substitute the unitary operator here. So that means we have this 326. And then if we first multiply this right factor into the parentheses, then we get this. And here we have the differential operator. So if we differentiate that, we get minus I e and derivative of lambda here as factors. So we can cancel I and e, but the derivative of lambda stays here in the equation. So, and if we now multiply the right unitary operator here into the brackets, then we get this, because here we have operator and inverse operator. These are scalar factors. So this is 1, and we have only a mu. And here, that's the same. The derivative of lambda is a scalar factor, and so we cancel out the exponential functions. And so we have this. So that means the transformed A is the old A added or subtracted by the derivative of another function, an arbitrary function. And now the gauge field. We have introduced a new field A to keep the formalism transformation invariant when we execute a gauge transformation. And here this field is a vector field, and we can say the formalism is gauged by A, so that we obtain the correct result, and so we call it a gauge field. But now there's obviously another field here in the physics of electromagnetism, and that means that we have to write new variables into the Lagrange density function. So here we have the wave functions and of course the derivatives, but now use the covariant derivative. And we have now as new variables the gauge field and of course the first derivative of the gauge field. So it must also possible to write down a term for the gauge field, for the electromagnetic field alone. And this term must of course be invariant under the transformations. And if we look for such a term, then we find this 329. That means we have for the Lagrange density function only for the gauge field, we have minus a quarter, f mu nu contravariant and f mu nu covariant. F is of course the electromagnetic field tensor, and that should be known from classical electrodynamics. That is d nu a mu minus d nu a nu. Or we can write that by using a commutator. Then we would have this. This must be a covariant index. This nu must be upper index here. Okay. And this is the only gauge invariant term with the first derivative of the gauge field A. And so it is necessary to use this term because there is no other one that works. And we can consider the transformed f. If we want to write down the transformed f, then this is then dA prime, dA prime. And then we substitute a prime. We have seen that is a plus the derivative of an arbitrary function. So we write a nu plus d nu lambda. And here the same in the second term, only exchanged indices here. And now we see here we have d nu lambda plus. Here we have minus d nu lambda. Here minus, so we can cancel out the lambda terms because the partial derivative is interchangeable. And so we have only d mu a nu and minus d mu a nu, and that is the untransformed f. Untransformed. And this is the untransformed f. So we see transformation invariance. That's okay. Then we consider the Euler-Lagrange equations of motion. We must now write into the variation of the action integral the covariant derivative here. We have seen only then we have invariance. And if we have a fixed A, then we consider only the fields psi, and then we can execute a partial integration according to this rule. That means we have for the f function this term. For the derivative of g we have this. That means g is now this integrated. There is no differentiation. And and from f to f, so the derivative of f, we have a d mu here in front. And so if we substitute that in the rule of the partial integration, then we have this 334. This term vanishes because the variation of the starting and end point it's vanishing. And yeah, here again we have an arbitrary parameter delta psi that is not vanishing. So the whole term is 0 if the term here in the braces is 0. So we can write this, and that is the equation for the Euler-Lagrange equations of motion. Or for the adjoint quantities we have this. That's the same, but the difference is we have now here a covariant derivative. And these two equations describe the interaction with the electromagnetic field, which we find here in the covariant derivative. And then for fixed psi quantities, then we have for the Euler-Lagrange equations for the gauge field, this. But here with normal derivatives, partial derivatives, if we would have a covariant D here, that means we would have another field in the D. That's nonsense. Here we have the usual partial derivatives. If we make now a calculation, though this term is here on the left side, and we can write this on the right side with a plus sign, and then we substitute the Lagrange density here by this term we have found. Here we must be careful with the co- and contravariant indices. Okay, we don't write here x. We know the A and F is dependent on the space coordinates. And so we have here covariant indices in the denominator. That means covariant indices in the numerator. And so we use the metric tensor G to make out of these two contravariant indices, alpha, beta, two covariant indices, gamma, delta. Then we can factor out minus quarter here, and then we write this d mu a mu into the brackets. Then in 340, we can factor out minus quarter, and we can also factor out the two G factors, because G is a Minkowski metric and this is constant here in the flat space, so we can factor out these two factors. And though we have in the brackets a product of two F tensors, and so here in the first addend we differentiate F gamma delta, and in the second term we differentiate F alpha beta. Then we substitute for F this with the gauge field A, and in the other term the same, but for the other F tensor. We have now here indices mu covariant, means contravariant in the numerator, and here we have two terms with covariant indices, and that's only the derivative here and here. That means the result is Kronecker deltas. That means we have here gamma covariant, mu contravariant, that is this delta, here we have mu contravariant, delta covariant, that is next, yeah, and so on. Then here for the next dA, and here the same, but here for the other tensor with alpha and beta, of course. And so we have this expression, 342. Then we can multiply the G tensors into the bracket, the parenthesis. So that means, yeah, here alpha gamma contravariant, gamma covariant. That means we get for the gamma here a nu, this nu here as the new index. The same for the next delta and for all the other deltas. So we have, instead of the deltas, now G tensors. We continue. We have here metric tensor with contravariant alpha nu. Here we have F with alpha beta covariant. That means that this alpha index becomes a contravariant V. And here this beta, together with this metric tensor here, becomes a contravariant mu index. That's the first one. And so that is the same for all the other terms. So we get here for this minus F mu nu. Then here the next one is a plus F mu nu. And then the last one is a minus F mu nu. Now we must know that the F tensor is antisymmetric. So if we have here F mu mu, then that is the same like minus mu nu. So we can here write plus F mu nu, and so we would have 4 times the same positive F mu nu. Yeah, we get a factor of 4 that can be cancelled with the factor here in front. And though we have only the derivative, okay, the minus stays here, minus derivative of the electromagnetic tensor. If we look at the electromagnetic tensor, here we have the explicit form of that in 348. Yeah, this equation 346 is true. These two equations represent the Maxwell equations. Yeah, where we have for this part of the Euler-Lagrange equations, we have E multiplied by the current J, and of course the derivative. Here we have a scalar product. It's a scalar product with a partial derivative. This is 0. And if we look at 316 here and 318 here, that's a covariant derivative, then we can write here this for the current J. Now, because of the formalism, 3, 3, 7 and so on, we can write here 350. This is an exercise for students. Show that the equation 350 is correct. The current J is gauge invariant, of course. We have this. And because of 327, where we have the transformed gauge field is equal to the old gauge field plus the derivative of an arbitrary function lambda, we must say we would have an indefinite number of solutions. To obtain only one solution, we make use of the free choice of a mathematical condition. We use the Lorentz gauge. That means, the scalar product with the differential operator and the gauge field is 0. The gauge field describes the free electromagnetic field. That means photons. And photons have now longitudinal or time-like component. Photons are only transverse waves. And so that means that the components A, O and A3 are 0. They vanish. Now we finish lecture 3. Next time in lecture 4 we will talk about Young-Mills gauge fields. Very important. For example, we describe isospin multiplets and so on. Thank you for watching. See you next time. Goodbye.